This project is about implementing the OFDM transceiver architecture in MATLAB. My name is Gibran Ali and this is my final course project for the course of Wireless Communications EEL 6509. So in this project what I've done is I've implemented the OFDM concept using an OFDM transceiver architecture, and I have explained each step of the transceiver architecture followed by the simulation which I've performed in MATLAB. So I'll start off with the overview of the concept, OFDM concept. That is what is OFDM? OFDM stands for orthogonal frequency division multiplexing. It is a technique which is used to increase the system capacity. It is also a solution for different wireless channel impairments, one of them mainly being intersymbol interferences. Intersymbol interferences basically work. For example, if you say intersymbol interference is basically caused by a multipath. A multipath is basically obtained by a signal being, for example, go-getter being reflected out of different objects. So if a go-getter is reflected out of a different object, say for example, and then after a certain time interval, go-getter is again reflected, then these two different go-getter symbols delayed by a particular time instant will interfere among each other, and the resultant symbol will be an intersymbol interference. So this is what the intersymbol interference is, and OFDM basically helps us to avoid these kind of wireless channel impairments and help by thereby increasing wireless systems capacity, which is generally mostly used nowadays in the 4G system. So how it basically does is divides the data rate of the symbol, and then it individually, also what it does is it divides the entire bandwidth of the channel into small number of subcarriers. So it individually modulates the reduced data rate with the individual subcarrier, and then it is transmitted over the channel. So that's the important part of the OFDM concept, that it divides the entire bandwidth of the channel into several subcarriers. Now there are certain advantages of OFDM. As I said before, that it's used to reduce the effect, or basically eliminate the effect of the intersymbol interference. What it does is basically, after we modulate the entire data into several number of subcarriers, what we do and send it over a multipath channel, the signal basically will perceive a multipath channel by a narrowband channel. So basically what's going to be like, it's like the frequency selective fading will be in such way that the flatness perceived by a narrowband channel overcomes the intersymbol interferences, and the frequency selective fading and the channel impulse response is diminished by the latter, which is the frequency selective fading. So that is how it removes the intersymbol interference. And another part is like it's got an advantage over equalization. Even the equalization could have been simpler to implement. In equalization, basically what happens, say you get a go-getter term for a particular time instant, and then a delayed time instant you get another go-getter. So what happens in equalization? What happens is like if you delay that particular symbol so that all of them arrange at the same, all the samples of the signal go-getter are arranged in the same time instant, and then we add it up, it's going to amplify the resultant signal. So if you amplify the resultant signal, if the noisy part of the signal will also get amplified. That's a disadvantage which we do not want. So as a result, we kind of avoid equalization, and as a result, use this OFDM concept in order to remove the intersymbol interference. So it's gonna interpret the multipath channel as a narrowband channel. So and as a result, the channel response is almost flat. As a result, there will be only one multipath per subcarrier. The disadvantages of the OFDM concept is it's got a very large dynamic range. That is, it's got a very large average, that is peak to average ratio, and is also sensitive to frequency errors. And as I said, equalization would have been much more simpler to implement. So it's a bit complicated compared to equalization. This is how an OFDM transceiver architecture looks like. This is the block diagram. So for our project, I'm going to explain each of these blocks in the transceiver architecture and run the simulation after almost each of these blocks and show you the plot. So this is an overview of the OFDM transceiver architecture starting from the transmission side. So at the first, what happens is, as we've learned in class, that the bits is basically converted into symbol, bits to symbol mapping is done, and then the message itself is modulated based on whatever modulation scheme we've been using, as QPSK or GMSK or QAM. The third step would be modulating it with the IDFT carriers. Now in this case, what happens is we modulate each sub-channel basically in frequency domain should be brick wall, but in time domain, a brick wall function would be an SIG function, which is very difficult to realize in a real practical system. As a result, the carriers which we use are IDFT carriers, and these IDFT carriers are orthogonal in nature. Orthogonal being that the IDFT matrix is orthogonal. So individual subcarriers are IDFT. So, and then after modulation with the IDFT carriers, we do a addition of cyclic prefix. Now what does cyclic prefix do? Now if we take a block of symbols of 0 to m and modulate with the impulse response of the channel, say length L, the total number of samples obtained will be m plus L minus 1. Now this last L minus 1 symbol will interfere with the next set of m plus L minus 1 symbols, because as a result of multipath, again another set of m blocks will be observed that will again be convoluted with the channel response, say length L, and then again we get a total number of samples of m plus L minus 1. So the last L minus 1 will interfere with the next set of received data which was received due to a multipath. So this will cause adjacent block interference, which is unrequired. So what we do is, one way of avoiding this particular condition is by zero padding the last L minus 1 symbol. Now this will be obtained as a result of reduced data rate. So which is again an unnecessary case. So what we do is the last L minus 1 symbols before transmitting is cut and copy pasted in the front. This is known as cyclic prefix, and as a result, at the receiver end, we again and then it's convoluted with the channel. So when we get the receiving output, we see that the convolution with the channel is, as a result, not a linear convolution but a circular convolution, and as a result, the necessary 0 to m symbols are unaffected by the cyclic prefix. That is, there is no intersymbol interferences in the 0 to m bits, and the resultant L minus 1 symbol is again removed, or rather L minus 1 sample is removed at the receiver end. And then at the transmission end, again after the addition of cyclic prefix, we convert the data from parallel to serial for transmission purposes. We send it through a high power amplifier, and then we do the cyclic convolution with the channel. So our simulation is basically going to implement each of these steps, showing data and plots of the data after each of these steps. At the receiver end, again we convert the serial data to parallel data for realization purpose, and again, as I mentioned before, we remove the cyclic prefix and we perform the FFT of the data. Now when we multiply, say for example, we got x0 to xm symbols, and then we multiply in the Fourier transform. When you consider the Fourier transform is basically a multiplication in the frequency domain. So when you're doing the convolution, so x0 when convolved with x, say impulse response of the channel will be, say, C0. So after doing the Fourier transform, it will be a multiplication of x0 into C0. Now as a result, what happens, we have to divide by the impulse response of that particular channel, say by C0. Now as a result, say for example, if C0 is very low and the channel was very bad, then the resultant x0 which is obtained, the symbol will be very poor in nature. As a result, if the noise is there in channel, it will be amplified. So based on provided bit error rate and the signal to noise ratio which is obtained from the waterfall curve, that is the required condition for the transceiver architecture, we will have to obtain that. So if it is a poor subcarrier channel, we may choose to reduce the transmission power of that particular subcarrier, or we may choose not to transmit over that particular subcarrier to begin with. So that is done, and then another receiver, and again obviously we'll do the demodulation of the data to obtain the final data. So mathematically, this is what an OFDM concept looks like in a mathematical terms. Say XT is the final transmitted data, and BI is basically this is sigma, because we're doing the modulation. So sigma of BI with WIT, and BI is the individual number of symbols that is being transmitted, and it's modulated with WIT, where WIT forms of A, which is A and P of T minus I of capital T multiplied by the exponential format. So here basically what happens, this A part is a result of the high power amplifier. Based on whatever modulation scheme we'll be using, we'll be choosing an amplifier accordingly. Then P is basically a resultant of a pulse shaper. A pulse shaper is basically required in order for transmission. That is the frequency, that is the bandwidth should be that the channel should have a band limited signal. Should receive a band limited signal, and also it should also follow Nyquist criteria. So that in order to avoid intersymbol interferences. So for that reason, the transmitted signal should be pulse shaped. And this is the exponential part, which shows a carrier. So omega I is basically the OFDM, implementing the OFDM concept, where each symbol BI is modulated with each individual carrier, subcarrier omega I, and this resultant XT is obtained. This is just the mathematical theoretical concept which has been used. So we use the raised cosine filter in order for pulse shaping. This which is shown by this particular graph, and these are the different role of factors. So for alpha equal to 0, we'll be obtaining a sinc function. This is again a spectra of an OFDM subchannel. This is how spectra of an OFDM subchannel looks like, and this is the orthogonality is shown in the frequency domain of the entire OFDM signal, consisting of all of the subcarriers. So we see that where the minimum point or the amplitude is 0 for a particular subcarrier, the second subcarrier's amplitude is maximum at this point. So this is how an orthogonality is obtained. Okay, so for simulation purposes, this is the experimental setup where we are using a total number of 128 data points, and the block set is basically kept to 8. So as a result, we'll be having a 128 data points divided into 8 blocks, 8 data points having a single block having 8 data points. As a result, we'll be having 16 rows, or rather 16 columns of total number of data set. And then the modulation scheme which we are using is QPSK, that is quadrature phase shift keying modulation scheme, and M is taken as 4. M is the variable where 4 represents the the constellation diagram. There will be 4 total number of available symbols. And then we also need to calculate the size of the cyclic prefix. For our simulation case, we have taken it to be 1, which is basically the calculated value based on the formula which we have been using in our simulation. And so the first part of the simulation is we generate a vector of random data point. As a result, a total number of 128. So this is the plot which is being obtained by the generation of 128 data. Now this is our simulation in MATLAB. This is the simulation in MATLAB. This is the MATLAB code which we have used, and as I said again, this is the experimental setup. M is taken as 4. Number of data points is 128. Block size is 8. So we'll be getting a block size of 8, and as a result, we'll be getting 16 columns. And then the length of the cyclic prefix based on this particular formula. And then 0.1 times 8 is rounded up with the ceil function to obtain as 1, and we calculate the number of IFT points. And at the transmitter end, again we generating a 128 size of 1 into 128 vector of random data, and after we run the simulation, hopefully we'll be obtaining all the plots. So I will be explaining in details of all the plots that's been obtained. So this plot which we see, this is the data generated. It shows total number of 128 messages, and this is a magnitude. So in my PowerPoint, I've put this plot in. This is 128 data generated. So this is the first result of the first part of the simulation, that is generating a 128 plots. So we perform after the data being 128 bit data generated, symbols generated, we perform a QPSK modulation scheme. Now the QPSK modulation scheme, this particular block diagram shows the QPSK modulation scheme. This is the in phase, this is the quadrature phase, and this is being individually modulated with the mixer, and this is the carrier frequency. subcarrier frequency rather, and this is the in phase, which is the cos component, the quadrature phase, which is the sine component, and then this is individually modulated, and then summed up to get the signal which is to be transmitted. So in the baseband, it's basically the bandwidth of the QPSK transmitted signal will be 0.5 times the data rate, and in RF it will be RF first null to null bandwidth will be equivalent of data rate, that is 2 into 0.5 into data rate, which is equal to the data rate. So bandwidth is equal to the data rate in RF mode. So this is the resultant QPSK modulation. In QPSK modulation, basically we'll be having four symbols, four possible symbols. So this is the constellation diagram. In phase and quadrature phase. So in phase is the cos component, and the quadrature phase will give me the sine component, and there will be four symbols. So each symbol, as a result, will have 2 bits of data, which is basically the concept of QPSK. And this plot is again obtained by obtained in MATLAB. This is a scatter plot. As we see, this is the plot which we have obtained, and this is again inserted in this particular PowerPoint presentation. And then next, next part of the simulation is, so this is the part where we modulate, we show the modulation. The next part of the simulation is performing IFFT. What we do is rearrange the data. We divide the data into blocks, block size of 8, and then we rearrange the data so that number of columns in this case will be 16 because we are using 128 data, and then we perform a data matrix of size 8 into 16, and then we perform IFFT of the data, and then this is the part we actually find out the starting of the cyclic prefix and the end of cyclic prefix and the block size. So it will start from 7 and then end at 8, and this is the case where we actually do the IFFT of the data, and then this is the IFFT matrix, and then we actually append the cyclic prefix before being transmission. So as I said before in the explanation, that we need to first do the IFFT, which is being performed here, and then add the cyclic prefix. So this is IFFT data by the cyclic prefix, and then we convert the data from, so after doing that modulation with the IFFT carriers and then addition of cyclic prefix, we convert the data from the from parallel to serial for transmission, which is done by this particular code, and then actual OFDM to be transmitted is obtained by this particular code, and as a result this is a plot which is being used to this is a plot which is being used to show the data being transmitted. This is the plot which is being used to show the generated OFDM data, and this has been inserted in my PowerPoint presentation as well. And this is the mathematical, this is just a theoretical explanation of what I just explained in MATLAB, and this is the mathematical formula for IFFT, for performing IFFT. And this is the OFDM after we convert from parallel to serial. This is the OFDM data which is being obtained. And as a result, in the next case, what happens? We pass the data through a high power amplifier. Now, high power amplifier is basically based on the QPSK modulation scheme used. So, QPSK modulation signal is basically for non-constant envelope modulation, and as a result, for this we require linear power amplifier. And for non-constant amplitude modulation, we could have used non-linear power amplifier, where non-linear power amplifier has high efficiency, and high efficiency leads to lower DC power consumption followed by a longer battery life. But in this case, since we are using QPSK modulation, we will be using linear power amplifiers. So again, in this case, we are showing the effects of the linear power amplifier and linear high power amplifier, which also has some amount of noise. And then in this part of the code basically computes the condition where you use the OFDM signal in association with the noise which is there in the high power amplifier, and the final transmitted data after passing through the high power amplifier is obtained and has been inserted in this particular curve. So this is the final transmitted OFDM signal which is being transmitted over the particular channel, which is also obtained in the MATLAB curve. Then next what happens is we have to establish a particular channel. In our channel, for our paper, we simulate the effects of small scale fading in MATLAB and its effect on the generated OFDM signal. So what we do is we create a multipath channel for our simulation purpose. Multipath channel. So this is creating a complex multipath channel, and the reason why it's being done is because we show the effects of frequency selective fading for a wideband system in a channel so that it can cause multipath. So that is why we create a multipath channel. And what it basically does is we have to show the effects of how an OFDM concept handles multipath interferences. We know that multipath causes intersymbol interferences and frequency selective fading. so that the flatness perceived by a narrowband channel overcomes the former and the channel impulse response diminishes the latter. That is why in order to show the effect of an OFDM, we need to create a multipath channel. And also this channel, multipath channel, also has AWGN channel, associated wide Gaussian random noise. So this part of the code makes it an AWGN channel, adds noise to it. So this is where the channel is established, and then we will show the receiver side of the data. This code shows the receiver side of the data. At the receiver side, I mentioned again, we convert the receiver side, we perform a similar step, we get to receive our original data. So we first convert the received serial data to parallel, we remove the cyclic prefix, and then we perform the Fourier transform of the resultant signal. So as I have explained here, all these steps by step, it's shown that we first convert the data to parallel form. This part shows, or the MATLAB code shows that we remove the cyclic prefix, and then we perform the fast Fourier transform. And then we convert the data to serial string, and we get the data, or rather the scatter plot of the received data. This shows basically again the in phase and the quadrature phase, and total number of symbols here we'll be finding is 128 symbols, and each symbol will have 2 bits of data. So this is the received data which we obtain, but our job here is still not completed. We need to first, then again, to get the final data, we need to demodulate the data, and then this is shown by this part of the curve where we perform the demodulation of the data. And after performing the demodulation, because we have done the QPSK modulation, we need to perform the demodulation of the data, and this is the resultant 128 symbol shown. The graph of 128 symbols shown, which shows the total final demodulated data. So this is, so if the system had certain kind of bit error rate and signal to noise ratio requirement, we could have found out that particular case by comparing their entire symbols with the received data and the final and the transmitted data. This was the transmitted data, the data generated with the final received demodulated data. We could have found out the signal to noise ratio and bit error rate, and it should have hopefully satisfied the necessary required conditions. So basically this project was to successfully simulate the OFDM transceiver architecture and plotting the results at every stage of the architecture, so which was successfully done in this project. And it also shows the effect, simulation also shows the advantage of the OFDM concept in mitigating the effects of the intersymbol interference and its advantage over using an equalizer. Even though the implementation of an equalizer could have been simpler, there are also certain research opportunities in OFDM, that is, there are still a certain amount of problems still facing OFDM concept, that it has got large dynamic range, that is got a large peak to average ratio, and is also very sensitive to frequency errors. The simulation performed in this paper has achieved in providing a clear understanding of the fundamentals of the OFDM transceiver architecture, and I hope I was successful in doing so. And I will include the project report in the IEEE format along with the code, PowerPoint presentation, and the YouTube video as part of my final project. It has been a great learning experience. Thank you.